Welcome to the today's session. In the previous session we have seen the timer 0 interrupt configuration using the LED blinking. It is going through the peripheral interrupt expansion module. In today's session we will see the configuration and usage of the ePWM module, enhanced pulse width modulator. Here also we can generate the interrupts using the ePWM for the ADC start of conversion, and if we want any interrupt we can do that thing also we will cover. Basically in this session we will focus mainly on the generating the gate pulses. For example, in this converter G1 and G2 are there. We should not turn on both the switches at a time. For that we will use the deadband. For example, during the rising edge we want deadband of 2 microseconds. During the falling edge we want 4 microsecond delay. This configuration, how to set such kind of thing, we will explore in this session. Okay, let's go to the technical reference manual. Go to the 15th chapter, enhanced pulse width modulator. Okay, this is the overview. I am assuming in the class this explanation has been covered. Here we have the time based module. It will have the counter. It will count from 0 to TBPRD period value, and it will reset. Okay, here counter, compare, action qualifier, event trigger and interrupt. We'll at the end we will discuss briefly about this, and we will use the deadband configuration in this session mainly. And there is a trip zone. Here for example there is a clock fail or any speed related thing, or any overcurrent protection. Overcurrent, some if we detect overcurrent, then we can block the gate pulses. Here trip zone module, using the trip zone we can block all pulses by the modulator. Okay, let's go to the in this session we will focus on the ePWM1 module. Okay, the ePWM1 module is connected to the ePWM1A and 1B, connected to the GPIO 0, GPIO 1. Okay, in the LaunchPad, in our LaunchPad there is a pin number 40 and 39. Okay, these two pins we have to configure as a ePWM in the GPIO peripheral muxing. For that we should go to the TRN GPIO chapter. Here peripheral muxing. For GPIO 0 and 1 we want to configure as a ePWM 1A 1B. For that you have to GPA mux register, you have to put 01. That thing I am doing in the code. First in the main function I am calling the GPIO configuration. In the GPIO configuration I want to choose GPIO 0 and 1 as a ePWM pin. For that actually I am doing that one here. Before that I am disabling the pull-ups. In the first session we have discussed GPIO means every pin has a pull-up disable software adjustment, that one. Okay, that one I am disabling for the GPIO 0 and 1. Actually this is not required. If you use GPIO as input, in that case we have to enable the GPA pull up disable, we have to enable. For the sake of formality, I am doing just here. Okay, in the GPA MUX1 register, I am what is the address of GPA MUX1 register? I think these things I need not to cover. GPA MUX1 offset 6, offset 6, base is 7C00, that means 7C06 is the address of GPA MUX1, and we have to write 01, correct, right? Here 0101 means 1015, right? That's why I have written here GPA direction register. Actually this one, the moment you choose as a GPIO as a ePWM, it by default it will act as a output, but for the sake of formality I am doing here again. To act as a output, we have to write GPIO 0 and 1 as a 1, correct, right? The direction register, you can see, to act as a output we have to write with 1, that's why I am writing 1 1, that is 3 I am loading into this register. This is about the GPIO configuration for these 2 pins. Okay, next we will see the ePWM configuration. Okay, for you should have idea on the clocking, how ePWM module getting clocking. For that just go to the chapter 3. Here clocking chapter is there. Here in this figure you can see the here ePWM clock is there. How this ePWM clock is been deriving from the main clock. Here PLL system clock is there. This is 200 megahertz by default. Okay, PLL system clock here came. Here there is a division by 1, division by 2 by selecting this bit. Okay, where is this bit? We will see what is the default. Okay, oh sorry, I want to search for this bit. Okay, press enter. Here by default it is divided by 2. Okay, here bit number in this peripheral clock division selection register, ePWM clock division is here. If you see, by default PLL system clock by 2. Okay, that's why here PLL system clock I have written 200 megahertz. ePWM clock I am writing divided by 2 because there is a by default by 2. Okay, that's why ePWM clock I have written here 100 megahertz. Okay, after that, after getting this ePWM clock, here again we can this clock will go to the ePWM module. There go to the 15th chapter. Here here time base module is there, right? Sorry, here, yeah, here time base counter, that ePWM clock will be used by the time base counter all the purposes. Okay, here time base counter, time base clock will be there. That one again we can derive from the ePWM clock. okay, those time based clock frequency, those are such that kind of those things we will see. Okay, next yeah, in ePWM configuration, right, second one is ePWM configuration. Here here before here we have to enable the ePWM module clock. Okay, we have to enable the ePWM module clock. Before doing that, we have to stop the time base counter. We have to stop, then enable the ePWM clock for this module. Okay, then start the time base counter. That's why for stopping the time base counter, there is a peripheral clock 0 register is there. There you have to write accordingly. Okay, let's go to that register. Here clocking, in the clocking chapter, here system control registers are there, expand it. Here CPU system clock registers are there. Go to the peripheral clock register 0. Here you can find that time base clock sync. This bit we have to stop the time base counter, we have to put 0. To start the time base counter, we have to put 1. Okay, what is the base address? Offset is 22. Base address is, yeah, where is the CPU system clock registers? Base address is 5D300. Okay, offset is 22. But our that register, that bit in the upper 16 bits. That's why offset 23 for this for this 16 bits. That's why I am writing here 23. Okay, success. I have stopped the time base counter, and now I have to enable the clock to the ePWM module 1. I am using right now only ePWM 1 out of 6 modules. We are using first module, ePWM 1. Okay, for that go to the CPU system clock registers. Here peripheral clock register 2, go here, and here we have to enable the ePWM 1 gating, clock gating for this ePWM 1. For that you have to write 1. Okay, what is the offset? 26. What is the offset? 26. What is the base? Base is same. Okay, 5D300. Okay, 5D300 plus offset 26. In this register I am writing 1 to enable the gating, clock gating to the ePWM 1 module. Again I have to start my time base counter. Okay, to start time base counter, again I have to write here bit number. Earlier we have seen, right, that bit we have to write as 1. Okay, 4 means go to the CPU system registers and peripheral clock 0. Here you can find that here 1 means 4, right? That's why I am writing here 4. Okay, this is about the clocking to the ePWM module. Next we will go to the ePWM module. Go to 15th chapter. Okay, here initially I am time based control register is there. There we in this session, one more thing I want to mention is, in this session we are using up down counter, up down triangle. Okay, carrier is there. that one we will update in the certain register, compare A, compare B registers. Okay, this is the time base counter. Initially it starts from 0, it will count up to time base period, and again it will decrement to the 0. Like that it will generate the triangle. Okay, the maximum number of counting, that is the time base period, TBPRD. This is the time base counter counting. Okay, let me explain this. Here time base clock is there. In each count it will take this much time period, time base clock time period. Okay, based on that frequency we can set, derived from the ePWM clock, frequency of the time base clock. Okay, here what is the time base period? This time base period we have to mention during the configuration. Okay, for example carrier frequency, this is carrier frequency, right? Time period of carrier waveform, that one. This what is the value of TBPRD we have to calculate. Okay, if you see this, T carrier equal to 2 times of TBPRD into, for each count, time base clock time period. Okay, from this expression we can calculate TBPRD count, how many counts we have to count to get this much carrier frequency. Okay, here from this equation TBPRD equal to TB clock frequency, this one, TB clock frequency divided by 2 into F carrier. Okay, F carrier means 1 by T carrier. Okay, similarly TB clock equal to 1 by time period of TB clock. Okay, this is the calculation of the TBPRD. While deriving the time base clock from the ePWM clock, these two registers we have to these two bits we have to configure. Okay, we will use default values only. In default this is 2, this is 1. For that we will see these two bits available in the time base what is that called, time base control register. Okay, time base control register, ePWM registers, go to the where is ePWM registers, time base control, first one, base address is for ePWM 1 4000, for offset is 0, time base control register. Here see clock division and high speed clock division. Here by default this is on reset 1, division by 1, here division by 2. Here note that 1 is there, we should not disturb that. Okay, and counter mode is we are going to do up down count mode. Okay, for that what is the number we have to load in this register? Bit 1 and 0 is 10. Okay, this is 10 and this is 001. 7th bit is 1. Okay, 7th bit 1 means 8 2, right? That one. In the offset 0, base address is 4000. In the time base control register we are loading 82. That means this 8 came because 7th bit is 1 for the this bit, high speed clock division bit. Okay, sorry, yeah, and 2 came because here up down count mode we are going to use. Okay, what is next? Time base counter, initially I am resetting to 0. time base counter offset is 4. Okay, that's why I'm writing 4000 plus 4 offset, clearing the time base counter. Next, time TBPRD. Yeah, one more thing here, by 2, right? Let me go to here. Here high speed clock division by 2 is there. That means what is my time base clock? ePWM clock by 2. ePWM clock by 2 into 1. That one I am doing here. I got 50 megahertz. Okay, for that what is the carrier frequency? TBPRD equal to TB clock 50 megahertz divided by 2 into carrier frequency, in this case 5 kilohertz we are considering, and I got 5000 counts. Decimal number, hexadecimal is 0x1388. that one I am loading here. What is the offset to the time TBPRD here? TBPRD here, yeah, here TBPRD offset is 63. Okay, in 4063 I am loading 1388 TBPRD for 5 kilohertz. Next is action qualifier control register. Where is that? Yeah, action qualifier control register. What is this? During the, suppose this is the time base counter, that is triangle, compare A, compare B, registers are there. This is the modulating waveform, like for sine PWM, sine wave, for square PWM, square wave we have to load into the compare A register. Okay, that means in the timer, for example, for every time ISR in interrupt service routine executing every 20 microsecond, in every 20 microsecond we will update the modulating waveform to the compare A register, and the ePWM module will generate the gate pulses as per our logic mentioned in the action qualifier register. Okay, in the action, suppose during the up count we want to generate PWM, we want to reset, and while down counting, compare A, while down counting we have to set. Okay, this, then we will get gate pulse like this, high, low, and here again high. Okay, for that during up direction we have to reset, during down direction, counting down direction, we have to set. For that, understood, right? Here action qualifier module, submodule is there. Here counter number will come here from compare A. When means counter compare will generate the signals, right? Whenever counter equal to compare A, signal will come. At that instant, what to take the action? That's why action qualifier. Okay, that register we are setting now. That's it, right? Action qualifier control A register, offset is 40. Okay, go to that register. Here several bits are there. For example, here 0, action when time base counter equal to 0, action when counter equal to TBPRD. Here action when time base counter equal to compare value, and up count. Here U means up count, D means down count. Okay, what we need is we will load our modulating waveform in the compare A. In this session we want to generate 50% duty ratio. For that we will load compare A register continuously with half of the TBPRD. Then we will get the 50% duty. Okay. For that what is our logic? During up direction CAU, when counting up direction, whenever time base counter equal to compare A, we have to clear. Okay, 0 1. And down direction we have to set 1 0. What is the number? 1 0 1 0 1 0 0 1. Okay, 9, right? Yeah, 9. That's why offset is 40. Okay, in the action qualifier control register we are loading 90. That means this during up direction we are clearing, during down direction we are setting. Okay, action qualifier completed. Then our signal going into the deadband module. In the deadband module we want to set rising edge, we want 2 microsecond delay, falling edge 4 microsecond delay. We have to go to the deadband module now. Where is our deadband module? Here deadband module is here. Let's go to the how to configure. For example, we have generated one gate pulse like this. Okay, whenever time base counter means we have generated the one gate pulse out A. With this we will extract 2 pulses from this gate pulse, that for IGBT 1 and 2 in our circuit. Okay, how? For first IGBT we will delay the rising edge, only delay the rising edge. Then we got this pulse. Okay, this we will give to the IGBT 1. Okay, we have to for IGBT 2 complementary pulse we want. Okay, with complementary gate pulse to this pulse. Okay, with deadband. Okay, how to create complementary pulse? For this pulse delay the falling edge 4 microsecond, make it delay. Okay, from this gate pulse I got this pulse. This is 4 microsecond, for example, falling edge delay. Earlier rising edge delay, this is 2 microsecond. Okay, now we got the falling edge delay. This waveform we have to negation, invert it. That waveform shown here. Okay, this is for IGBT 2 lower IGBT, this is for IGBT 1 upper IGBT. Okay, these two are complementary with rising edge delay of 2 microsecond, falling edge delay of 4 microsecond. This can be adjusted based on the setting. Okay, how to do that setting we will go now. For calculating here, right now we are using time base clock equal to ePWM clock divided by 2. Okay, here just this is how many counts we have to delay. That number of counts we have to calculate right now. Okay, that calculation I have shown here. DVPRD deadband rising edge delay, we want 2 microsecond. 2 microsecond. How many counts I have to do to delay this much to get 2 microsecond? How many counts I have to delay the delay? That number of counts I have to give in the DBRED, deadband rising edge delay register. Okay, here time period of time based clock is 1/50 megahertz, that is 0.02 microseconds. I got 100 counts. Corresponding hexadecimal is this one, 0x0064. And deadband falling edge delay, I want 4 microsecond. For that I need to delay 200 counts. Corresponding hexadecimal number is 0x00C8. These two registers I have to write. I have to load. What is the offset for that? Offset is dBFED rising edge, dBRED offset is 51, dBFED offset is 53. Okay, go here 16-bit register. Okay, 4051 rising edge is 4051. I am loading with 64. And what is the falling edge delay offset? dBFED 53. Okay, in 53 I am writing our this number 00C8. Okay, before that yeah, we have discussed this, but we have not set what is that deadband logic. Deadband, go to the deadband register. Here we have generated first pulse. Here, come here, this pulse we have at the ePWM XA1A. Okay, from this we will extract two pulses, one complementary each other with deadband. Okay, for that we have deadband rising edge delay module and deadband falling edge delay section. Okay, what is our logic? Just rising edge delay by 2 microsecond, that register we have loaded already. Just we have to tell rising edge by rising edge delay. For telling that, here see how default switchings mentioned here. We want here, we have to make this switch to here. This DBRED we have loaded. Okay, that one like this. Initially take this signal, S4 is 0, delay by rising edge delay register. According to that it will come. S8 is default 0. Okay, then put this S1 to 1, position 1. Then this will available at the GPIO 0, output A. Okay, in the second signal, how to generate? Delay the falling edge and invert it. Okay, delay the falling edge according to the DBFED register. Take the same signal and default only. These need not to change, and delay the DBFED according to that register, and negate this. To invert this signal S3, you have to make 1. Okay, then S0 leave it as default, then this also leave it as default. Okay, that means these two bits we have to change. No, this not this one, S1 and S3. S1 has to put to position 1, S3 has to put to position 1. The respective register is DBCTL, deadband control register. Okay, we have to go to the deadband control register and make bit S1 to 1, S3 to 1. Okay, go to the ePWM registers. Where is the deadband control register? Deadband control register, deadband control register. Yes, here offset is C. Okay, here what to write? S3 1, S1 1. Okay, S1 1. Where is S1? Here, S1 switch, S1 switch 1. Okay, S0 0, 1 0. Here 1 0. What is S3? S3 1. Here 1 0. Okay, correct, right? 1 0 1 1 telling. We have to go to the time base counter. Where is deadband? Deadband. Here bit 0 is S0, bit 1 is S1, bit 3 is S2, bit 4 is S3. Okay, bit 0 is default is 1, that one we should not disturb. Bit 1 is we have to change it to 1, that means this is 1 1. Bit number 3 is 0, default is 0. Bit number 3 is 1, that means 1 0 1 1, 1 0 1 1. One 0 1 1 means 1 0 1 1 B, right? That one I am writing here. Here you see bit 0 S0, bit 1 S1, bit 2 S2, bit 3 S3. That's why I followed that. Now 1 0 1 1 B, that one I am loading into the deadband control register. Okay, our deadband configuration ready. Deadband rising edge delay, falling edge delay we have given. That's all. Here compare A register we have to load. That one I am loading every interrupt service routine. I am loading compare A register. What is the compare A register offset? Here compare A offset is 6A. Okay, 406A, that is here 2 registers are there. I mean 32-bit register we have to load into the upper 16 bits. That's why offset is 6B. Okay, that's why I am loading into 406B. This is I want 50% duty ratio. I am loading with half of the TBPRD. That calculation you can do. Okay, actually I am using in this code, I am using timer 0 interrupt for every 20 microsecond. I have set this timer 0 is going through the peripheral interrupt expansion module. Those configurations we have covered in the previous session. That's why I am not discussing here. Just I am changing the I am changing to the for every 20 microsecond. Earlier we have used 0.5 second. For 20 microsecond I am getting 0 F A 0. This one correct, or means maybe I have not decremented one count. That one you check. I guess here 9F should come. Okay, this calculation you can get it from the previous session. Okay, here whenever this interrupt occurs, it will go to the ISR, it will execute. This is acknowledgement like earlier. Okay, actually the ePWM module will generate the gate pulses independent of our code execution. Okay, if you load compare register, even though you have not been updating for every timer interrupt routine, for every ISR, even though if you don't, even though you are not updating in updating compare register for every 20 microsecond, one time if you load, it will generate the PWM pulses. Okay, this is about the code. I will share this code with you people. You can now we have to check our results in the DSO. Okay, digital storage oscilloscope. I am assuming you will at your any lab, go to any lab and access DSO and check your pulses. That is very important. Okay, since this is recording, I will show using my camera. I will show the waveforms. Okay, let me go to the here. I want to access camera. Okay, yeah, now I want to here DSP is there. I have connected here. You can find pin number 40 and 39. Okay, and ground. I have connected the oscilloscope. Oscilloscope is there. This cable I have connected to the pin number 40. This one. Okay, this ring, this pink color ring is there, right? Here I have connected this, and another probe here. Ground is there. This ground wire I have given to here. Here ground I have connected. Here ground I am taking, and pin number 39. Pin number 39 I have connected to the another channel here. Okay, channel number 2. Okay, that ground and same I have chosen, both are connected to the same ground. Okay, now we will load our program. Okay, now I have loaded the program but not running. Now I am clicking on run button. Okay, here we will see the gate pulses. Okay, now I am zooming out. Okay, these are the, let me check whether I am recording this or not. Yeah, these are the gate pulses. Here you can observe 5 kilohertz, 5 kilohertz, 3.2 volts, correct, right? Here, okay, here 5 kilohertz and 3.12 volts. Okay, the rising and falling edge delays we will see now. Okay, here we will put scaling 1 microsecond per yeah, here see 1 microsecond, right? Each division, second per division is 1 microsecond. Okay, now go to trigger, rising edge. This is in channel 1. Channel 1, this is rising edge delay. Okay, 2 microsecond here. Here 1 microsecond. 1 microsecond is the second per division. Okay, here 2 divisions are there. 2 microsecond rising edge delay. What about falling edge delay? This one. Falling edge delay is 4 divisions, right? Here 1, 2, 3, 4. 4 microsecond falling edge delay to the channel 1. Okay, this is the gate pulses. Okay, now here you can check all your configurations. I am not showing here. Now this is about the ePWM module gate pulse generation. Okay, one more thing I want to share is here event trigger submodule is there. Event trigger submodule. For example, we are using ADC. In the next session or sometime later, we will see the ADC. For that, it requires start of conversion A, start of conversion B based on these requirements. For that, these pulses can be generated from the event trigger module and interrupt, and event trigger and interrupt module. Okay, it develops this signal, generates this signal based on the time based module, and based on the counter equal to period, counter equal 0. Based on these signals, counter equal to compare A, counter equal to compare B. Based on this logic, it will generate the these signals. And here digital compare, based on our digital compare means here for protection purpose, overcurrent, speed or clock fail, all this protection is there. Based on this also we can generate the interrupt or start of conversion. This is interrupt. Okay, it is going via peripheral interrupt expansion module. For configuring this ePWM interrupt, for example, we want counter equal to TBPRD. At that time we want this interrupt, or based on this counter equal to period logic we want to generate SOC signal. Okay, such kind of things we can get using this event trigger interrupt. Okay, okay, for that what we have to do, go to the peripheral interrupt expansion module. Where is that? Yeah, peripheral interrupts, right? Here, where is that? Our interrupt table is there, right? You know, right? Yeah, here for example in this session we are using ePWM 1. Okay, what happening? Yeah, ePWM 1. Okay, it is coming into the group 3 interrupt 1. Okay, you have to group 3.1, group 3 interrupt 1, you have to configure your these things. Okay, these things we have covered in the previous session. Just in earlier session we have seen the group 1 interrupt 7 timer 0 interrupt. In this, for this group 3 interrupt 1 ePWM 1 interrupt, you have to configure. Okay, similarly ePWM 1 trip zone interrupt, if you want you can do. Okay, this is about the today's session. Okay, trip zone, and here several applications has been mentioned here. Applications to the power electronics, you go through this. Okay, it will helpful, means 4 or 5 cases they have taken and demonstrated here how to configure those things. For example, ePWM 1 and ePWM 2 is there. We want both carriers should be locked, right? For that what we have to do, we have to make one ePWM module as a master and other ePWM modules as slave. Okay, for master time-based counter we have to lock other time-based counters. For that, for example, ePWM 1 as a master, counter equal to 0, at that we have to lock the next time-based counter also. We can make phase shift between the triangles also, but we will lock both triangles. Okay, how sync out sync in is there, according to those bits you have to configure. Okay, those example code has been given in the control sheet, you can go through that. Okay, here also I guess some example program they have given. Control sheet I have mentioned, that is not assembly, that will be in the C code. Okay, if time permits we will see. Okay, this is about the today's session. Okay, thank you.